Okay, so welcome to this presentation where we'll speak about old-growth forests and how to identify them with airborne laser scanning. So for a bit of context, old-growth forests, they're vanishing everywhere in the world. And if we take the example for boreal forests of Quebec, for example, we see that old-growth forests are naturally abandoned because fire rate is not that high, especially in the commercial forest, because most of fires are above the northern limit of commercial forest. And in fact, in contrast, the harvest represents a very higher disturbance rate located within larger areas of the commercial forest and creating a very strong loss, in fact, of the forest, a loss of fragmentation, because the overall disposal rate is way higher than that of fires. And so we need to better protect our forest to maintain its function and service. But very another issue is that we still often underestimate the complexity of our forest. Because we know that during forest succession, the forest will change of structure, the change of composition of habitat with time, including when old-growth status reach. Because in Quebec, for example, we consider that old-growth forests are all forests above 100th century. But in fact, this definition is too simplistic because we know that with time we'll have still structural changes, we'll have still changes in habitat, we'll have still changes in species present, and even after 200 years of age, we can still show very strong changes in time. And the same for carbon stock, it increases in time and it can still continue to increase if the palification or then stabilize, but still, depending on forest age of the succession stage of growth forests, we can have very strong differences. And just considering them as one big homogeneous wall is not sufficient because it can lead to very strong issues when trying to harvest to protect our growth forests. And another issue now is that in Quebec, we use photo interpretation mainly to survive forest, to know. And this method is not accurate enough to identify the diversity of old-growth forests. In a recent study, we observed that old-growth forests for very different ages were all classified almost the same way, like old but even age, because trees are small, they're not many tree species. So it was the same class for every type of old-growth forest. And so to solve this issue, here we try with airborne laser scanning to see if we can do better, quicker, and easier than photo interpretation to identify this age-induced diversity of old-growth forests. So to do this, we chose the three territories in Quebec, Canada, and selected for several reasons. And first, it was the presence of a fire that burned 100 century ago. So forests that are old-growth, but just at the beginning of the old-growth stage, or reference early old-growth forests. But nearby, there are also two protected areas of late old-growth forests, which are vertically not burned since at least 250 years. So here we have two reference areas to train our model to try to distinguish between different types, different succession stages of old-growth forests. And also, we also there's still some intact areas of old-growth forests within a landscape of harvest, where the forests have not burned since at least 155 years. So areas to train our model. And finally, we have also access here to some validation data. So first, 88 plots from the provincial forest survey of the province of Quebec, but also 100 kilometers west, we have access to around 60 field plots from a field survey dedicated to the survey of old-growth forests, so more accurate, more precise data. So shortly, for data preparation, we divided the landscape in 1 hectare tiles. And we use not raw ALS data, but we use a canopy height model derived with ALS data to define 7 ALS indices representing the horizontal and vertical structure of the forest. Then for analysis, we use one of the forest model. We try to classify the reference on early and late old growth based on the ALS indices. And also we use an iterative approach with resampling to try to evaluate the influence of spatial articulation on possible sample bias in our results. And at each iteration, we predicted for the undefined old growth forest within the study area and for the field plots, the probability of a type to be classified as late old growth forest. And to simplify the result, we use 3 different classes, so predicted early old growth forest, so under 33% of probability, predicted total growth forest, so an intermediate class between 33 and 60% of probability, and predicted late old growth forest, so where the probability was above 60% to be classified as late old growth forest. And what we obtain is a very good model, very high accuracy, because as we can see, the error rate was very low, was under 5%, where the almost perfect area under the rock curve, and also the influence of the spatial interpolation was almost null, because spatially explicit and spatially non-explicit model were providing almost the same results. And it shows that ALS data are very efficient to discriminate structurally the early and late algal forests, to have a very clear picture of the structure. And then, if we when we saw field validation, we obtained fascinating result, because first, for the when we observe a provincial survey plot, we observe no difference in time since fire between the different predicted classes, with an age ranging around 150 years for each class. However, using the algal field plots, or more accurate, more precise plot, we saw here a very clear gradient of age. So with a younger forest, relatively younger, with 170 years old being the predicted early algal forest, and the predicted late algal forest exceeding 200 years old. And when after we observed the structural forest for the untitled forest, we saw that for the reference and predicted early algal forest, there were clear structural differences between these two classes, which imply difference in successive stages. In fact, the predicted early algal forests were for most a more advanced successive stage than the references, because we saw in the structures evidences of the beginning of gap dynamics, or reference plots of the first post-fire cores by new shade-tolerant cores. However, for the late algal forests, we observe no structural differences between the reference and predicted tiles, meaning that this model was very efficient to identify forests which were at least older than 250 years. So then, when we apply this model in the study area, what we observe is that we are able to identify very large and continuous areas of late algal forest. So here in orange, in red. And so we observe here more than 17,000 hectares of late algal forests, or forests that are up to above 230 years old, and representing often blocks of more than 1,000 hectares. And they are in fact in a younger matrix of forests, but here younger is relative, because as I said before, these blocks of very old algal forests were located within matrix of forests which are often older than 150 years. And this illustrates well the complexity of algal forest areas, because in the same block of algal forests, we can have very strong differences in the forest age within space. And finally, well, we can see that on this map, there is no block of predicted transition algal forest. And this is because in this case, this class was mostly an interface between early and late algal forest from different succession stages. So it's not a succession class per se, but it seems to be more an interface between forests defined by different disturbance histories. So what we can say for the result is that ALS data are very, very efficient to identify the algal diversity and discriminate algal forests defined by different ages or different succession stages. And just using, in fact, canopy height models and not raw ALS data, we were able to obtain a very, very good result. So it would only help to use this method because it would be less resource consuming. In addition, here we use reference algal areas rather than just field plots to parameterize the model. So all fires are protected areas. And as we saw it, it has been a very efficient method to discriminate that algal forests for undefined algal styles. And finally, we obtain results which are ecologically consistent. So it corresponds to what we can expect from a stand and landscape structure of algal forests. It's a very positive output. And in fact, the main limit was the issue of field validation data, because remember, what we saw is if we use the professional survey plots of the most common field plots in Quebec, we saw no difference in time since fire. Whereas when we use a field plot dedicated specifically to study of algal forests, we saw a strong difference. And an issue is that provincial forest survey plots are known to be strongly biased when forest age exceeds 150 years, because the way the data is taken is like 3 dominant trees called at 1 meter height. And this method it's a strongly unfit forest edge in old-growth forest and mostly in old-growth forest, because dominant trees are really the oldest trees, and taking a car at 1 meter height, it will strongly understate tree edge because you miss forest separation. And in contrast to a detailed growth survey with more tree samples for different canopy strata is more efficient, but also these data are way rarer because they're more costly to take. But then the issue is that now it will be very hard to parameterize and to validate models within Quebec if we cannot rely in the most current field data, which has the provincial forest survey plot. And so it shows that we need to expand our database of field plots that are dedicated to the survey of old-growth forest to create better models to identify old-growth forest structure and diversity. So, as a conclusion, we can say that this method is the first step for more detailed mapping of old-growth diversity. Just providing a difference between early and late old-growth forests would be very useful for managers and for conservationists, because right now, as I said in the introduction, a way to see old-growth forest is way too coarse, way too reductive. And then we can still refine our approach. And just for example, for the same selection stage, we can just use clustering to try to identify then specific structures and specific tree species composition to have a more detailed vision of old-growth forest. But a main limit is maybe that right now this method is dependent on all fire and protected areas, because they're useful to have access to many data to parameterize the model, but then the location of all fire is relatively random, and there are not so many protected areas in the boreal forest. And so we need to see now in the future to which extent we can use this method in larger areas, and to which extent it will stay relevant at the scale, for example, of the boreal forest of Quebec. Nevertheless, what we provide is a very important tool for old-growth protection and conservation, because here I show the impact of forest harvesting within the study area in the last 30 years. And as we can see, forest harvesting was a very rapid, a very quick, and a very important loss of old-growth forests. But in fact, we don't know what we have lost. We don't know what was the impact of restoration of old-growth forests. We don't know what are the characteristics of remnant old-growth forest. So using LS data, we can now provide better tools to have a more accurate vision of old-growth forests, what we are losing, what is remaining, and then we can better know, we can better define protection and restoration objectives. So thank you for attention. If any question, you are welcome.